pressure drop calculations for the cooler in steady-state environment. In dynamic environment in AspenHYSYS, we can predict the pressure drop across the heat exchangers more realistically using the resistance factor. In Dynamics tab, you can find out the overall K, which is the overall resistance factor, and when you check the box, then it will predict for you the pressure drop in various conditions. But in steady-state environment, this is not available. So what we need to do is to implement this manually. How to do it? The first step is to calculate the resistance factor. So preferably use the design case to calculate the resistance factor from the following equation. So here K is the resistance factor and m dot is the mass flow rate, rho is the mass density, and delta P is the pressure drop. When we calculate the resistance factor for one of the cases, more, as I said, preferably the design case, then you can calculate the pressure drop and implement it in your spreadsheet, export it to your heat exchanger, and when you change the flow rate and properties for the inlet fluid, then the pressure drop will be updated. One important note here is we need to be careful about the units. So what units you use to obtain the resistance factor. So when you are also calculating the dP, it should be based on similar units. Otherwise, when you change the units, then the K should be updated based on the new units. Now we can do an example in the previous simulation, which we worked on in the previous sessions. This is our design case. We already made the spreadsheet in the previous session. And heat exchanger, and also as I show you in the dynamic tab, if you check this box, it will give you the more realistic pressure drop when you put the accurate overall resistance factor. So what we do in dynamic simulation actually is putting for one of the cases, for example the design case, we put the pressure drop first, we activate that, and then calculate K, and then stop the simulation, and then we remove the checkbox for the delta P, and then we activate the overall K. So then, based on that, we can have more accurate pressure drop calculation. So now, based on that formula, we need the mass flow rate. So I need to bring the mass flow rate here, density, bring it to the spreadsheet, and also the pressure drop which we had. So it's 0.7. So for now, I just do the calculation. So we have the resistance factor calculation. So let's use the formula, which was m dot, which is A4 divided by mass density B4 multiplied to pressure drop C4. So this is the equation we obtained here. Let's once more check the equation. Yes. So now I need this value, which is 6964, almost 0. So I just use that number, delete this formula. I need to implement a new formula. So bring that value. So this is our resistance factor now. So now we want to calculate the pressure drop based on this information and export it to this part. So I remove this and later implement that again. So the formula was 1 per rho, which is the density, multiply to mass flow rate divided by resistance factor. So almost 0.7. Since I didn't copy the number, I just wrote it. So it was some differences. Still is okay. So now I can export this one. Let's see if I can export it by drag and drop. No, it doesn't work sometimes. So I just bring the cooler, say E100, and search for pressure drop. Since this cooler is a simple cooler, it doesn't have the both tube side or shell side or hot side or cold side. So we have only one side. So that pressure drop is the only one. So this is implemented and exported there. So let's close the spreadsheet and do some example. So if I reduce a bit the flow, so we have to see that the pressure drop will be reduced. So let's reduce it to 9,000. So pressure drop reduced from 0.7 to 0.53. And then go to 7,000. 0.54. 5,000. So also let's see if the anti-surge is working properly. So I can open the curves just to see it. I want to gradually go to full recycle, see what will be the pressure drop in the full recycle because of the hot gas coming to the heat exchanger. So in this case is 0.6, so it was lower than our design case. In some cases, the full recirculation case can be dominating for pressure drop. And also when you are changing the condition for one existing cooler or a compression loop, and especially changing the bundles for the heat exchanger, for the compressor, then you need to check the hydraulic capacity of your heat exchanger, and implementing this resistance factor is a very good way to predict the pressure drop more realistically. Maybe not 100% accurate, but the error should be very small based on my experience, and also checking with the calculations using HDRI and the other softwares. I found it a very reasonable pressure drop calculation. Thank you for attending this video, and in the next session we will talk about anti-surge valve sizing.